Dr. Lee for joining. Hey, thank you for that, Tracy. Once again, our appreciation to Dr. Lee for joining in with us for our regular graduate seminar series. Dr. Lee is an assistant professor at the Department of Petroleum Engineering at the University of Houston. Before joining the University of Houston in 2017, she had been working geological postdoc fellow at Energy Geosciences Division of Lawrence Berkeley National Laboratory since 2015. She received her PhD degree from the Petroleum Engineering from Texas A&M University and an MS and BS degrees from Energy Resource Engineering from Seoul National University in Korea. Dr. Lee, thank you once again for joining us. And I won't steal any thunder. I'm not going to even say your talk title. I'll leave that to you. And the floor is now yours.
Okay, thank you so much. You can see my shared screen.
We can see it.
Yeah, so thank you so much. My name is Kyung Jae Lee, and thank you very much for inviting me. And I'm very happy to give a seminar at Petroleum and Geosystems Engineering Graduate Seminar. So my topic today is identifying a new source of lithium from petroleum source rock brines. So these are the outlines. So I will start from the introduction, brief research experience and scope of mine. And then I will start the lithium in high demand with energy transition. And then we will go into the lithium in petroleum source rock brines. And then if the time allows, I will show you some of the results of Bayesian scale simulation of lithium in petroleum source rock brines. So first, introduction. Just briefly, I'm doing the computational and experimental research on fluid transport and heat flow in porous and fractured media. And I'm doing the pore scale to the reservoir or Bayesian scale modeling. And my research projects are focusing on the clean energy transition, such as origin, fate, and transfer of critical minerals like lithium in source rock brines. That's today's topic. And also safe nuclear waste disposal systems and kerosene chemical additives interactions and their impact on the surface chemistry change, and also water and rock interactions. So these are my research scope. So when we, in our group, we are starting from the micro scale study, both on experiment and the numerical modeling. So we figure out physical and chemical phenomena and apply inter-array scale inversion of reservoir properties. And then ultimately we want to develop field scale simulation model with minimized simplifications and assumptions for various engineering processes in the subsurface energy systems. And we also do some statistical learning analysis for oil and gas production optimization or minimization of water use or air emissions. So I'm basically the modeling person, but I have a small lab in our department regarding the characterization of rock and fluid. So we have validation and then input provision method in our lab so that we can directly use them in our modeling and simulations. So today's topic, we will start the lithium in high demand with energy transition. So in terms of energy transition, we need to know about the climate change, and then how do we know about the climate change? This data is coming from the NASA. And when we see the carbon dioxide level in the atmosphere, some people say that the carbon dioxide level in atmosphere is going up and down through the very long years. But current level of carbon dioxide is very high, abnormally high. And then it's very true that we are on the challenge of the carbon the climate change. And also by these high carbon dioxide concentrations in the atmosphere, we see many evidences on the Earth, such as global temperature rise and warming oceans, and also especially in the Arctic regions like decreased snow cover, glacial retreat, and shrinking ice sheets or declining Arctic sea ice. Also, even in the big cities like Houston or San Francisco, we see the sea level rise, and then many regions are facing the inundation risk. And also, as we saw from the last year, like a winter storm, extreme events are very often occurring, and also there is ocean acidification. So there are many evidences that we face as evidence of climate change. So in order to tackle the climate change and in order to make sure the decarbonization, we need to think about the energy transition. The energy transition is defined by the significant structural change in energy system. And when we see this chart on the right-hand side, this chart shows the global energy transition investment from the 2004 to 2021. So this one shows where we put most of the money in the energy transition sector. So as we see, the renewable energy has the biggest portion, and then electrified heat and the electrified transport followed it. And both electric vehicles and the renewable solar and wind electricity generation rely on the lithium-ion energy storage or lithium-ion batteries. We can say that lithium will be playing more and more significant role in the energy transition. So when we see if the lithium supply will be satisfying the demand, we can see this forecast. And then we are here around between 2020 and 2025. And then at this point, we have more lithium supply than the demand. But when we go to 2030, soon we will be catch up by the demand, and the global lithium supply will be less than the demand. So we will need to think about how we will be able to enhance and diversify the source of lithium from the nature. And natural sources of lithium, they are typically in the two types. First is the solid minerals, and the second is the brines. So the minerals means usually lithium, aluminum, silicate in diverse minerals like spodumene, pegmatite, or hectorite. And the brines, lithium can be dissolved as a cation, and then we can produce lithium from the continental brines, geothermal brines, oil field brines, or recently known source rock brines. So these kind of different types of lithium are distributed like this globally. And we see that South America has the biggest sources of lithium from the brines. And currently, the US has only one active brine production for the lithium. So let's just see the global lithium supply chart here. So when we see the countries providing the most of the lithium to the market, we see the Australia and Chile, Argentina, China follows it. And then we have a very small amount of lithium supply in the USA. So former president issued an executive order in 2017 to increase the critical minerals, including lithium, supply in the US. So US Department of Energy puts a huge amount of money to develop the critical minerals from US. So it was the motivation of my interest in the lithium. And as a petroleum engineer, I found some very interesting research about the petroleum source rock brines as a source of lithium. So when we see the petrolithium concept, petrolithium itself is not a very new concept because lithium has been produced from the conventional oil field like a Smackover, and lithium was highly abundant in such brines. But from the unconventional shale, we recently found that high concentration of lithium, like 80 to the 230 ppm, has been found in the produced water from the shale formations, such as Marcellus Shale. So it was like 3 to 4 years ago, it was found. And then we did some ion chromatographic analysis in our lab regarding the Green River Shale, including the 30 volume percent of kerogen. We leached like two weeks, and then we did the ion chromatographic analysis, and so huge amount of lithium ion in it. So, okay. So although the source rocks can offer substantial opportunities for sustainable and renewable utilization of lithium for energy storage, their successful production relies upon subsurface phenomena relevant to the origin, fate, and transport of lithium, which has been unknown yet. So my motivation is to elucidate those scientific and engineering phenomena relevant to origin, fate, and transport of lithium in the petroleum source rock brines. Then is the source rock brines will be able to provide a significant amount of lithium. So when we see the shale play in the USA, including the Marcellus shale here, if we can figure out the unknown factors about the lithium in the source rock brines given by the big area of the shale play in the USA, we can say that it can be providing some good method for the diversification and the enhancement of the lithium supply in the US. And when we calculated the lithium amount in the Marcellus brines, we find that it's enough for the 100 years of the US lithium usage. So in order to figure out more about its unknown factors, I started from some hypotheses. So I was thinking that why the lithium, abundant amount of it is petroleum source rock brines. And then these source rocks are defined by the shale rock, including the immature or mature types of kerogens. And then the biggest event that source rock can go through is one of the biggest events is the kerogen maturation. So I try to see the many sources of the shales and their lithium content in the solid phase and the relationship between the total organic carbon and the lithium solid phase amount. So when we see the type 1 immature kerogen of Green River Shale and Marcellus Shale, type 2 moderately mature kerogen bearing shale, and then diverse oil fields with overly matured kerogens or oil and gas, we find that there is a very strong positive correlation between the total organic carbon and the lithium in the solid. So we can say that if we have a higher TOC, and then we could also find that higher lithium content in the solid and also lower kerogen maturity. And because we are all petroleum engineers, but in order to be at the same page, I just try to introduce you about the kerogen. So organic rich shales are composed with kerogen, mineral contents, and void spaces. And kerogen in oil shales or the organic rich shales is geologically immature solid forms of hydrocarbons, and it can be converted to oil and gas by artificial heating. And it's when it is heated above 300 degrees of Celsius temperature, it will release a number of fluid and solid components, including oil and gas, and then also inorganic elements. So this figure shows the world organic rich shale resources, and then United States has the most of the organic rich shale immature kerogens or mature kerogens in the world. So if we can figure out the connection between the lithium geochemistry and then kerogen bearing shale, I believe that US will play a significant role in the future lithium market. So in order to figure out those unknown scientific factors, we need to see how the components are there in the petroleum system and how we can connect it to the lithium geochemistry. So in order to determine the locations with high concentrations of lithium in the petroleum source rock brines as a dissolved carrion, we need to consider the entire petroleum systems, such as starting point of kerogen conversion and fluid release from the source rock into the reservoir rock. Actually, in the shale, reservoir rock is also shale, but lithium, release the lithium and then dissolve it in the water, it can flow through somewhere and then accumulate it somewhere. So my project's objective is to figure out the location of the high lithium content source rock brine in the petroleum system. Actually, I have some very good award from the NSF. It's about the Career Award, and it's about creating this new sustainable source of lithium in the petroleum source rock brines. And this Career Award is composed of two components. The first one is the research, and the second one is the education. So in the research, we have three research objectives: to figure out reaction mechanisms of lithium from kerogen decomposition, and secondly, figure out the transport phenomena of lithium containing water through the pores, and then accumulation of lithium in the brines. And in the educational component, we are working with the STEM students in the great Houston area, and then also Energy Institute High School students for the computer modeling with the very simple mathematical correlation equation. And also we are working with some industrial companies for the actual production of lithium abundant petroleum source rock brines from the Marcellus shale. So ultimately, we want to provide a source rock brines as a significant one of the new source for the lithium supply, such as in addition to the currently providing sources of continental brines, pegmatite hectorite, oilfield brines, and then geothermal brines. So let me go into specific topics. So the first topic of identifying the reaction mechanisms of kerogen thermal conversion releasing lithium. So here we want to experimentally identify the elemental and isotopic distribution of lithium before and after the kerogen thermal conversion. So when we see the structure of the kerogen bearing shale and the lithium, some of the lithium are directly attached to the kerogen. It's called the organic lithium. And then some of the lithiums are just attached around the minerals. So it's called inorganic lithium. And my hypothesis is that if kerogen conversion in the geologic system occurs, this immature kerogen becomes mature kerogen, and then it expels fluid and solids into the pore water. And then because of the kerogen decomposition, we will see the mineral redistributions. And then in addition to the organic lithium, inorganic lithium can be released. So that's my hypothesis here. And in order to figure out these reaction mechanisms, we are analyzing the elemental and isotopic distributions before and after the kerogen pyrolysis. So these are our kerogen pyrolysis unit. And we analyze the kerogen-bearing bulk rock and also the isolated kerogen to test the impact of coexisting minerals on the reaction, and also to distinguish the inorganic lithium release and then organic lithium release. So in order to do that, we are collaborating with the Geochemistry, who are helping me to do the analysis of ICP-MS for the elemental analysis and the multi-collector ICP-MS for the isotopic analysis. And in our laboratory, we are doing the TGA, DSC, GC analysis for the reaction kinetics from very low temperature around 100 degrees C until the very high temperature of 900 degrees C. So because our project started in the last June, it's still ongoing the first year. And but we found some very interesting findings. So lithium concentrations and analysis of the bulk rock and isolated kerogen from Green River Shale by ICP was done. And then we figured out how the lithium is initially distributed. So the Green River Shale, including the immature type 1 kerogen, has the 230 ppm of lithium in the bulk rock as a solid phase. And then when we do the closed system acid isolation of the kerogen, we see that significant amount of the lithium is gone, and we see very little amount of lithium are directly connected to the organic matter kerogen. And even for extractable organic matter, it has even smaller amount of the lithium. So we can find that most of the lithium is inorganically bound at the initial time, or acid extraction during the kerogen isolation removed the organically bound lithium. So we are also collaborating with the Rice University around here. So they provide us the time of flight secondary ion mass spectrometry, tough SIMS analysis tool. And we saw the initial kerogen-bearing shale powder pellet. We scanned it, and then we find the distributions of lithium and then some kind of organic connections, potential connections. So we are still analyzing it, and we are finalizing the initial amount of inorganic lithium and then organic lithium. And then we are preparing the publication. So I hope that the journal will be published soon. And also we finished the hydrous pyrolysis. So we will be analyzing the solid phase products. And then we also gathered the fluid phase products. And then if we analyze the lithium elements and then isotopes in each phase, we will be able to elucidate the reaction mechanisms with the kinetics. So that was the research topic 1. And then research topic 2 is the pore scale modeling to characterize the transport of lithium through the pores. So here we conduct computational modeling of the interaction between water containing lithium and the rock. The host of the lithium in the rock is the clay, such as smectite. And then by the cation exchange, lithium can be attached on the rock surface, usually the clay surface, or the lithium already attached in the clay can be released into the water. So we want to figure out these relationships through the pore scale modeling, and we developed the open form-based pore scale simulators. So this is just some numerical algorithms. So there are 2 typical methods to do the pore scale modeling by using open form. And I know that many professors in UT Austin are doing this research. And one method is to couple our open form with the Freak-C or like a crunch top, and then simulate the reactivity transport. And one another method is just working on the source code to develop our specified simulation models. So we are working on the source code and develop the specified pore scale modeling tools by ourselves. So in this method, we need to go through the subsequent equation solution. So when we see the flow chart, we first need to see the mineral compositions to figure out the reactivity of mineralization and dissolution of lithium, which is depending on the clay fraction and then morphology, because they are affecting the cation exchange capacity. And then we solve the continuity equation for fluid and solid phases, because the lithium mineralization and dissolution includes some mineral changes, and we can see some potential rock morphology changes. And also next we solve the advection diffusion equation or the mass balance equation for components to solve lithium concentrations in each phase of fluid and rock. And then we solve a momentum equation by Darcy-Brinkman-Stokes equation, which is applicable for both for fluid and solid zones, so that we can figure out the fluid velocity. So this is the proof of concept example in this research topic of pore scale modeling. And then this digital rock image of a Niobrara formation is coming from the digital rocks forum of Dr. Prodanovic. And then in order to test that if our numerical algorithm is feasible or not, we just try to run the proof of concept example using just a single mineral model. So this pore scale model includes the millimeter scale domain with the components of a micrometer scale elements. And then this is actually about the calcite dissolution, but we are modifying our code to change the functionality from the calcite and acid reaction into the lithium cation exchange reactions. So we see that if our rock morphology is very different around pore connected pores, we see that the fluid flow pathways are significantly affected by that. So by doing so, it's a very quick and efficient. So we could figure out that our numerical algorithm is technically feasible. And then by integrating the experimental findings into the pore scale modeling, we will be able to simulate the lithium cation exchange through the pore scale modeling. And then the third research topic is Bayesian scale modeling to characterize the accumulation of lithium. So this is the later phase of this project. And then we will need to integrate the first research topic of experimentally known reaction mechanisms. And then second research outcomes of a pore scale transport phenomena. We will develop our own simulation code to figure out a whole system of the petroleum source rock brines relevant to the lithium. So we are developing our Bayesian scale simulator based on TUF codes by using my expertise as a TUF developer in the Berkeley lab before. And then this numerical simulator includes 15 mass components of water, heavy oil, light oil, methane gas, mixed hydrocarbon gas, carbon dioxide, kerosene, and different types of cokes. In order to include the whole procedure of kerosene conversion, and then the relevant lithium relevant components of a lithium ion, sodium ion, which is cation exchangeable with lithium, and then sodium including clay, and then lithium including clay in the three phases of the fluid phases and the one solid phases. So the kinetic reactions are including whole kinetic reactions of kerosene decomposition, 7 reactions, and one equilibrium reaction of cation exchange between lithium and then sodium. They are included in the high fidelity Bayesian scale modeling tool. So the different thing between the Bayesian scale modeling from the pore scale modeling is that we can solve now for the whole equations of mass balance equations and the energy balance equations at once by applying the Jacobian matrix and the fully implicit solutions. So we include the whole findings from the research topic 1 and 2 about kerosene conversion and then mineralization and dissolution of lithium, and then heat exchange by the reactions. We could figure out how the system is behaving. So this page shows the proof of concept example run using the homogeneous rock and fluid system. So because we are still at the early stage of the 5-year project, so assumptive values of microscopic phenomena and characteristics are used just to check if our numerical algorithms are technically feasible. So we try to simulate lithium, which is originally embedded in the kerosene-bearing source rock, is released into the surrounding reservoir rock and transport through the lithium. We described that. And then the locations with the high concentration of lithium can be determined from the spatial distributions of lithium mass fraction in the formation brines. So this one shows the whole these after this whole mechanisms starting from the lithium release from the kerosene-bearing rock, fluid transport during the cation exchange, and then accumulation in the brines. So it's just a conceptual model yet, and we didn't consider the horizontal permeability or other properties or lithology heterogeneity yet. We see that the lithium is going down by the gravity segregation of water and the hydrocarbons upward. So we see that 10 to the minus 4 or around 100 ppm of the lithium is found from the brines. So next, the last chapter is the Bayesian scale simulation of lithium in petroleum source rock brines. Even though this is the last chapter of our research project, we did some conceptual design and modeling to figure out the most important factors we need to focus on in our project from now on. So we considered this 2D conceptual model containing different lithologic zones of a source rock containing high organic matter, impermeable rock above, and then reservoir rock. It's also the shale, but with a lower amount of the organic matter, and then impermeable rock here. So these are the system properties and initial conditions. And then because in the simulation, we cannot run until the geological time scale, it's a million year unit. But now we introduce the simulation time scale by equating the reaction rate constant of a geological condition multiplied by the geological time scale and equating it to the simulation scale reaction rate constant and the simulation time. So in order to run in the feasible time range, we adjust the temperature range of the geothermal gradient into the higher temperature, so that we will be able to run, for example, like 3 million years in the simulation time of like 3 days. And then in order to compensate the fluid transport, we do the same thing for the diffusivity. So by equating the diffusivity and the geological time, and then diffusivity in the simulation scale and the simulation time, we could figure out the compensated permeability and then run it. So these are about how we compensate the experimental, simulation condition and the geological conditions. And then we consider the sodium ion mass fraction in the aqueous phase and sodium lithium equilibrium coefficient and the lithium stoichiometry from the kerosene decomposition as follows from the Green River Shale findings. So these are just about we develop our high fidelity with a minimized assumption and simplification numerical simulators. So we consider every fluid properties computation methods. And then also because we are considering the changing amount of the solid and the fluid phases and its components, we have developed comprehensive functionalities regarding the interactions between fluids and porous medium in the dynamic conditions. And also these are mathematical equations we are considering, such as mass conservation, energy conservation, and chemical reactions as a source and sink term for mass and energy conservation equations. And because we are solving after constructing the Jacobian matrix to solve the whole primary variables at once with the most advanced method, we are developing the residual equations. So these are showing how we put the convergence criteria. So now we try to investigate the impacts of various factors on the lithium concentrations in the water. So we did some local sensitivity analysis by coupling the PEST protocol to our reservoir simulation model. So we figured out a few input parameters of with a potential impact on the lithium concentration in the water. So the input parameter includes the lithium stoichiometry in kerosene decomposition reaction, and sodium lithium equilibrium coefficient, and then sodium clay mass fraction in the solid phase, and lithium clay mass fraction in the solid phase, and sodium ion mass fraction in the brines at the initial condition. So each of them are expected to impacting the lithium dissolved in the water, like a positive effect and a negative effect. So for example, if we have much amount of lithium clay in the system, the lithium attached on the rock will be dissolved in the water through the transport. So it can be having the positive impact on the lithium dissolution and then accumulation somewhere to be produced. And then our output variable is a lithium ion fraction in brines, and those are scaling factors for local sensitivity analysis. So we first did the numerical simulation for at the 4 observation points of inside of the source rock at the higher deposit, and then lower depths, also kerosene bearing source rock, and the reservoir below the source rock, and then reservoir somewhere far from the source rock. So this base case and then increased lithium stoichiometry and active lithium sodium equilibrium, increased sodium clay and increased the lithium clay and increased the exchangeable cations are there. Each of the impacts are analyzed. So we see that increased the lithium stoichiometry from the kerosene decomposition significantly increased the lithium inside of the brines as a dissolved format. And also, if we have a very active lithium sodium equilibrium, then lithium can be more attached on the rock, and then we will see very small amount of lithium in the brines. And likewise, increased sodium clay will have the opposite, the similar impact to the more active lithium sodium equilibrium coefficient. And then if we have increased lithium clay amount or more amount of exchangeable cations in the water, it means that those exchangeable cations will be attached on the rock and the lithium will be dissolved in the water. So we will see more lithium will be dissolved in the water. So by going through the scaled sensitivity analysis, we figured out at each observation point about the most impactful factors to be studied. So when we are figuring out, so for example, if we are producing from the high depths of the source rock shale, we will we may want to just see the lithium stoichiometry because it only has the very high impact on the lithium dissolved in the water. And same here in the observation point 2 at the deeper depths. And then at the observation point 3, now in the reservoir rock outside of the source rock, we see that other factors becomes also very important, such as sodium lithium equilibrium coefficient and sodium clay fraction and the lithium clay fraction, as well as sodium ion fractions. So these are what we will be focusing on, the different rock sources at the different positions. And at the reservoir rock far from the source rock, we find that the factors affecting the cation exchange is more significant than the lithium stoichiometry from the kerosene bearing rock. So by considering these different factors affecting the lithium dissolution in the water, we are working with the industrial partner, and then we will more focus on each of the important factors at different positions. So this is the summary of my talk today. We are trying to seek to identify a new source of lithium in the petroleum source rock brines. And we provided the paradigm shift to turn the source rock brines into a source of lithium. We are still trying to working on it. And then understanding of release, transport, and accumulation of lithium in source rock system will enable the enhancement and then diversification of domestic lithium supply. And by elucidating the most influential parameters affecting the production potential of lithium in source rock brines at different positions, will be used to prioritize the factors to be researched at our later phase of the project. So this is my the end of my talk, and I want to have any questions or comments.
All right, Professor Lee, thank you very much for your insightful presentation, your lecture here today. I want to first of all open it up to any of our students, undergraduate or graduate students that may have questions. Don't be shy. All right, while our students are thinking, I'll open it up to anyone who attended today, faculty and students, to ask any questions.
Can I ask a question?
Please, Dr. Mohanty, please.
Okay, so my very nice talk. I really enjoyed it and I learned something. My question is lithium a product of some kind of geochemical reactions, or it just happened to be there with the kerosenes?
Yeah, thank you very much, Dr. Mohanty. And yeah, the lithium is what we are considering is the lithium, the physical dissociation from the inorganically bound sources and the organically bound sources. So it's more like a physical, physical dissociation in the clay, because it's kind of just exchanging the cations from the interlayer of the clay and the dissolved one in the water. So I would say it's just a simple exchange between the cations, like lithium between lithium and then magnesium, or lithium or sodium, lithium and then calcium ions, and not other complex reactions are relevant.
Thank you.
Dr. DiCarlo, I saw you had your hand up.
Thanks, Michael. An interesting talk. I didn't know the Marcellus had so much lithium. That looked like it had the most lithium of the brines you were looking at. Is that correct? Next, please.
So the Marcellus shale, yeah, it's found to be having very high concentration. Yeah, 80.
Which one had the highest one, I guess, was the question again for your slide, early slide? Was it or is it some other shale?
Oh, I think you're talking about, let's see.
Green River. Yeah.
Yeah, that's different actually. This is the y-axis is the solid phase. So it's before coming into the liquid. So it's the original place of the lithium and in the rock. And
okay,
then,
so again, like what Dr. Mohanty was saying, it's coming from the, and you were saying it's coming from the kerogen, basically.
Oh, but there was my initial assumption, but as we did the research topic 1, we conduct the research tasks, and then we find that very little amount of lithium is directly bound to the organic matter kerogen, but most of them are directly bound to the inorganic matter clays. But during the kerogen conversion, because all the minerals are altering and then redistributed, we see that many inorganic lithiums are also released into the water.
Okay. I guess my one little question with the Marcellus is, I thought there wasn't much brine in the Marcellus. It's pretty dry for the natural gas resource there. Is that correct?
Yeah.
I wonder if it's just a more concentrated, a heavier brine have more lithium.
So basically, we have produced water from the deeper formation, and my collaborator, industrial collaborator, is purchasing the water from the oil companies to process the lithium from them. And even if it's a dry formation and we don't want to produce water, but somehow we produce water.
Okay, so
right?
there is water produced there, basically.
Yes.
Okay. I saw another question or hands up, so. don't
I
know.
did. I saw Brendan. Do you still have a question?
Thank you. My question was relating to the organically bound versus inorganic bound lithium. I was assuming the research was focusing on the kerogen decomposition, but my question was going to be why or how could you include the kind of evaporate basin concepts that most lithium is currently found in this research?
Oh, so you mean like vaporite, like salt, or like different
Yes.
types from shale, right?
Yeah, well, so like in Utah, there's a lot of lithium in salts and stuff like that. Is there any potential research?
Yeah. But my starting point is the shale. So yeah, in this project, we are only focusing on the shale. But yeah, I think other types of sedimentary rocks can be interesting as well. I just wanted to find the rock that only petroleum engineers can work.
Fair enough. Thank you very much.
We have a question from Dr. Delshad.
Hello, very nice talk. And the question I have is on your simulation, you mentioned you're going to use tough, and I'm assuming is going to be tough react. So you already have the reactions included. So what are the requirements, modifications that you need to make to tough to make it, suitable for the lithium problem?
So I'm not using the top react. I know how to use the top react, but it's very heavy, and I'm developing my own code from the very simple seed code of the top, and then it's very similar to top react, but current top react doesn't have for sure this lithium cation exchange between existing cation in the petroleum system. So it's a new capability. And in order to do with the top react, you will need to define one or two necessary cation exchangeable with the lithium, and then somehow you will need to put some rock type, assuming that it's the kerogen, but current top react doesn't have that capability.
So you really only need to include the ion exchange, but these are all going to be two component exchange, or you may have more than two?
Because we want to develop the high fidelity model coming from the kerogen bearing rock, and it's all about the multi-phase flow. And then if you want to start from just the cation exchange, I think, one cation which is in the interlayer of clay and one cation inside of the water. Yeah, I think that will be simplified and easy way. Yes.
Okay. Thank you very much.
Thank you.
Thank you very much, Dr. Delshad. Any other questions from the group? Dr. Prodanovich, I see you're off mute.
I am off mute to point out the chat. There's a question if the copy of the presentation could be shared.
Oh, yeah, I can share with you. Yes.
Thank you very much, Dr. Prodanovich. Thank you very much, Dr. Lee. We appreciate it. Anything else? All right. Dr. Lee, thank you very much for joining us. Our only regret is that we didn't host you here in person. So we've a rain check to have you down here in the 40 acres, okay?
Yeah, I hope so. Thank you so much. I really enjoyed.
Appreciate you sharing your knowledge with our students. All right, thank you.
Yeah, thank you very much, everyone.